Okay, hello everyone. Welcome to 130B Quantum Mechanics. So today we are going to discuss perturbation theory. So last time we have started talking about perturbation theory. Perturbation theory is a very useful tool in quantum mechanics to infer the solutions of quantum systems in the vicinity of, say, a known system. So the general setup is like, suppose I know the property of a quantum system governed by some Hamiltonian, which is called H0. And then, given that knowledge, can I use that knowledge to predict what should be, for example, all the eigenenergy eigenvalues and energy eigenstates of a different Hamiltonian, which is not so different from H0, which is only a little bit different from H0 by a perturbation. So this perturbation is supposed to be small, meaning that this lambda, which is a coefficient in front of whatever other operator that adds to the Hamiltonian, this lambda parameter is supposed to be a very small number. And because of that, you can think of it as a Taylor expansion of a function. Suppose you know the value and all orders of higher order derivative of the function at a single point, you can basically predict the behavior of the function in the vicinity of that point in power series of the distance of a point from the reference point. So that distance or that deviation is basically this perturbation lambda. So that's essentially very similar ideas. And for that, we basically have two types of problems to solve. One is called time-independent perturbation, which focus on questions like eigenstates and eigenenergies, or eigenenergy of the new Hamiltonian. The other one is about time-dependent perturbation, where we not only are interested in this eigenstate, because eigenstates actually are time-independent. So for time-dependent problem, we are more curious about the time evolution operator. So we also want to know what is the effect of adding a perturbation to the system. What is the effect on its time, on affecting the time evolution of the system? Okay, so that's basically the general framework. And so today we are going to discuss the first topic, which is about time-independent perturbation. And in that topic, in that subject, the main goal is to understand eigenstates and eigenvalues, how that it is affected by the perturbation. Okay, so let's be more concrete, and then let's look at a simple example. In this simple example, we are going to start from a qubit. Let me remind you that qubit is a two-state system. It's it's a very simple quantum system whose Hilbert space is two-dimensional. So in this two-dimensional Hilbert space, any operator is represented as a 2x2 matrix. So this H0 will be a 2x2 matrix, and lambda will also be a number, and V will also be a 2x2 matrix. And in this example, we are going to take H0 as the Pauli matrix Z, and then V as the Pauli matrix X, such that when you put them together in this H0 plus lambda V, this lambda-dependent perturbed Hamiltonian can be written in the basis of 0 and 1 as something like this. Because this sigma Z is basically this 1 and minus 1, and the sigma X will be a 1 here and then another 1 here. But because it is multiplied by the coefficient lambda, so that lambda goes to these two different places. So this is the Hamiltonian we wish to solve. We want to diagonalize this 2x2 matrix and find its eigenvalue and eigenstate. So that's the problem we wish to answer. Of course, because this matrix is now lambda dependent, so we expect that the solution of eigenvalue and eigenstates are all lambda dependent. They all depend on lambda. So that's why I put the lambda in every one of them. And then I use a plus and minus sign to denote that this 2x2 matrix will have two eigenvalues. One eigenvalue, actually the larger eigenvalue will be denoted as an E plus, and the smaller eigenvalue will be denoted as E minus, and the corresponding eigenstate will be denoted as a psi plus or psi minus. Since this is a 2 by 2 Hamiltonian matrix, it's very simple to actually, you don't need perturbation theory in this case because it's even exact solvable. There's no problem. You use Mathematica to find its eigenvalues and eigenstates. So these are the results. So these are the eigenvalues. You can have analytic expressions and then the corresponding eigenstates. So you can see eigenvalue depends on lambda, and then eigenstate also depends on lambda. And then eigenstate is always a linear superposition of the two basis states. For the qubit system, there are only two basis states, 0 and 1. So any physical state, any quantum state in this system must be a linear superposition of them with linear superposition coefficient. Although in this case, the linear superposition coefficient is quite complicated, but it is still just a combination. And our goal is basically try to understand the behavior of these eigenenergies and the corresponding two eigenstates in the small lambda limit. So now you can see this solution actually holds for any values of lambda because it's an exact solution. You can take lambda to be even larger than 1, to be much, much larger than 1. It's no problem. It's exact solution. But you can see this already for this 2 by 2 matrix, the exact solution is so complicated. And then it's maybe not very useful because it doesn't give you much intuition what is going on, right? So that's why people are very interested in understanding like a Taylor expansion of these expressions. So perturbation theory at a very basic level is basically Taylor expansion. That is the fundamental mathematics behind perturbation theory. Assuming lambda is small, meaning that lambda is much less than 1, so we can expand the expression of eigenenergy and eigenstate in power series of lambda. And to remind you that the Taylor expansion is a formula that allows us to expand a function of any real number. So suppose I have a function as a function of lambda. I want to expand this function in the vicinity of lambda goes to 0. So that means I need to know what's the value of the function at 0, what's the first order derivative of the function at 0, and second and third and higher order derivative. Because when lambda is 0, then the function will just take the value of f of 0, right? But if lambda is small, then I can go away from this 0 and go. So let's say this function, the idea is that this function is a function of lambda. So at 0, maybe this function looks like this. And then if you know its first order derivative, which is this slope, then you can basically use the value of the function at this point and the slope of the function across this point to predict, for example, if I move this lambda away from 0 by a little bit amount, what should be the new value of the function, which is this 0 value plus slope times lambda. And of course, if you go further, then maybe higher order derivative also become important because you can see that the curve also is curving up. Then this second order derivative will also play a role, and eventually higher and higher order derivative will come into play, and then basically correct or dress the original value of the function, okay? So that's the idea of Taylor expansion. And the formula, general formula is like that. So as long as we know how to evaluate all orders of derivative of a function at a given point, we can basically write down the Taylor theory. The more derivative you can compute, the higher order you can go. That's the idea. So now we already have the exact solution, so we can do, although this is not the right way to do perturbation theory, but we can just cheat that we use the exact solution, and then we perform Taylor expansion on those solutions, and we can already see this result. And then, of course, perturbation theory is trying to provide us another way to calculating all these results. But I just want to show you what should be the final result, what should be the effect of perturbation theory. For example, when lambda goes to 0, we know what are the eigenvalues and eigenstates. If you look at this Hamiltonian again, now assuming lambda is 0, then the Hamiltonian is already diagonal diagonalized. And then this diagonal matrix element corresponds to the eigenvalue. And the two basis states are the eigenstate. So the eigenvalue should be +1 and -1. And +1 corresponds to the eigenstate 0, and then -1 corresponds to the eigenstate state 1 in this qubit system. So that is indeed the case. If you look at this Taylor expansion result, the eigenvalue has +1 or -1, and then there's corresponding eigenstate. The +1 corresponds to 0, and then -1 eigenvalue corresponds to 1. But then when you turn on lambda, these eigenvalues are going to change. And they are going to change in such a way that this 1 is being addressed by lambda square over 2 and so on, higher order terms. And then the eigenstates are also going to change because lambda is going to mix the 0 state and 1 state together. So once you have a non-zero lambda turn on in the system, then the original 0 state will have a little bit amount of mixture with 1. And then the original 1 state will have a little bit amount of mixture with 0. That's the leading correction. And then there's a sub-leading correction, try to correct back, which try to actually also put some coefficient, put some weight on the 0 state and so on. So there's some very complicated combinations of all these coefficients, order by order. And the goal for perturbation theory is to obtain the coefficients. For example, in this, we know the result must look like a power theory. So it must look like something plus lambda to the first power, second power, third power, and so on. But what are these like a coefficient, numerical coefficient like +1/2 and -1/8? Where do they come from, right? So the goal of perturbation theory is precisely to compute these coefficients in the power theories. And that amounts to compute the derivatives of energy eigenvalue at 0, at lambda equals 0, all orders of derivative. Of course, we wish to compute all orders of derivative, but in reality, in practice, usually we can only feasibly compute the first several order because the computation, although can be done, but can be very complicated as we go to higher order. But there's a systematic way to do that, which I will introduce. And then also we want to compute all the derivative of eigenstates. So that's the idea. Perturbation is essentially an iterative, perturbation theory provides an iterative algorithm to compute all these derivatives order by order. So you first compute the first order, and based on that result, you compute the second order. It provides an iterative way to do this computation. And once you know what are the derivative of energy eigenvalues and energy eigenstates with respect to lambda to any order you desire, then basically we can obtain all these results. And the computation of this derivative only relies on our knowledge about H0 and V, which is the unperturbed Hamiltonian and the perturbation. So now let's be more concrete and set up this problem at a very general level. So in order to describe the problem, so we need to start from this expression, which says that I have a perturbed Hamiltonian, which is related to the unperturbed Hamiltonian plus some perturbation, and with some small value lambda, which parameterizes the perturbation. This implies that this Hamiltonian, if you take lambda goes to 0, it will reduce to H0. And then if you take this Hamiltonian and take a first order derivative with respect to lambda, this operator will basically reduce to V. Because if you look at this expression, the first term doesn't depend on lambda, so it has 0 derivative. If you take derivative with respect to lambda, this goes to 0. And then the only term that depends on lambda linearly is this V. And then if you take this operator, you just think this operator as a function of lambda as well, because it's parameterized by lambda, right? So you can define derivative with respect to lambda to any orders, and then you can see all the higher order vanishes, because this is a linear combination of H0 and V using lambda, right? So the highest order term of lambda appearing in the Hamiltonian is only to the first order. So for the Hamiltonian as the operator, it only depends on lambda to the first order, and the derivative has a truncation, that it doesn't have higher order derivative. But that doesn't imply that eigenenergy and eigenstate also has that same truncation. In fact, eigenenergy and eigenstate generally has all orders of derivative with respect to lambda, given that even though the Hamiltonian only depends on lambda linearly, okay? So that's the idea. So in order to simplify the notation, you can see in this notation, I need to keep evaluating either my operator and derivative, or any orders of derivative of my operator at the point lambda equals 0, or maybe later we want to evaluate energy eigenvalues or eigenstates derivative also at lambda equals 0 point. So because we want to evaluate everything at lambda equals 0, so instead of to write this everything as a bracket with a 0 there to indicate I'm going to evaluate this object at lambda equals 0, I can ignore all this, or I can suppress all these notations and simply write the above formula as such. So in the following, whenever we see any expression without specifying what's the value of lambda, you should think that the expression is actually evaluated at lambda equals 0. So that's why we say that the Hamiltonian is basically at lambda equals 0 is this unperturbed Hamiltonian, and its first order derivative with respect to lambda is the perturbation. So that's the idea. So that's the problem set up. And then given this setup, the goal is to find the eigenenergies and eigenstates as a function of lambda. So I'm writing the eigenequation in this way that all the eigenenergies will be labeled by an integer n, and all the eigenstates will also be labeled by the integer n. So this En of lambda is the nth energy level. It is also a real number because Hamiltonian is a Hermitian operator, so eigenvalue is a real number that depends on lambda. And this n lambda denotes the nth eigenstate in correspondence to this eigenvalue. It is the state vector in the Hilbert space that can also change as lambda changes. So this notation I want to emphasize, it doesn't mean that n as a number depends on lambda. N is actually an integer label of the state. And then it doesn't depend on lambda. If you tune lambda smoothly, this label, this integer label doesn't change. When I say n lambda, using this notation, I mean that this is an eigenstate labeled by the index n, and the eigenstate itself, as a vector in the Hilbert space, has a lambda dependence. Which more precisely, it means that I can expand this eigenstate n in terms of a set of bases, let's say m. And then there will be a linear superposition coefficient that combine all the basis state m into this eigenstate n. And then the superposition coefficient now is a complex number. So that complex number can be a function of lambda. So our goal is basically to understand this function as well. So that's the two functions we are going to compute. One is this energy function, the other is the state superposition coefficient functions. And then we want to understand this behavior of this function in the vicinity of lambda equals 0 using perturbation theory. And in order to start, we also need to specify what we know. Because of course, you can't do any calculation if you have no knowledge about this, what is the original Hamiltonian and what is the perturbation. So these two formulas trying to specify what we know about the original, about the unperturbed Hamiltonian and the perturbation. So first of all, the unperturbed Hamiltonian, we know everything about this Hamiltonian, and we also know how to solve it, meaning that we know how to diagonalize the Hamiltonian and find its eigenstates and eigenenergies. So this is the starting point. We already know what a set of eigenbases of this unperturbed Hamiltonian. The reason I didn't put a 0 here is because, as I mentioned, whenever I didn't specify lambda value, it means I'm evaluating this Hamiltonian operator at lambda equals 0. So this is the unperturbed Hamiltonian acting on the state and then has eigenspectrum. Okay, so we already know all this. And then we also know how to expand this perturbation with respect to this basis state. Because this forms a basis state, and then any perturbation as an operator can be expanded as a matrix, can be represented as a matrix on this set of bases. And the matrix element, the mth column and the mth row and nth column matrix element will just be a scalar product between the bra state operator and the cat state. And then this operator is simply the first order derivative of your lambda dependent Hamiltonian. So this Hamiltonian is lambda dependent and it's first order derivative at 0, at lambda equals 0. Okay, so these are the information we know. We know what's En, we know what's Vn, Mn. We also know all these basis states. So suppose we know these three pieces of information, and now the goal is very specific. Using these pieces of information that we know at lambda equals 0, these are all information we know at lambda equals 0, try to infer what should be the new energy eigenvalues at a small lambda in power theory, expand in power series of lambda. Try to infer what are the correction of the states and how the states should be combined using these basis states in terms of lambda, okay? Is that clear? That's the problem set up. And we are going to solve this problem. And the solution actually relies on computing the derivatives of these functions. And although when you learn calculus, every time you take derivative, you need to first tell me what's the function, right? I tell you the function is sine of x. I know how to take derivative. How can I take derivative without knowing what's the function? That's the amazing part of perturbation theory that allows you to compute derivative without really knowing what the function you have at hand. The reason that we can do that is because there's an interesting theorem in quantum mechanics, which is called Hermann-Feynman theorem, HF theorems. So this HF theorem is derived as this. So let me talk about where it comes from. So first of all, we have an eigen equation. The eigen equation, you should think on both sides, everything depends on lambda. So that's why I can take derivative with respect to lambda on both sides. And then when I take the derivative, this is a matrix acting on the state, and the state vector equals a number times the state vector, right? So everything is multiplicative. On the left-hand side, you have a matrix multiplying a vector. On the right-hand side, you have a scalar multiplying a vector. But as long as it's a multiplication, the product rule applies. The product rule says that if you try to take derivative with respect to the product of two functions, then that equals to the derivative of the first function product the second one, and the derivative of the first function product the derivative of the second one. So that's why if you apply the derivative, it goes like this. This is the derivative of the operator. This is the derivative of the vector. And then that equals to the derivative of the number times the vector plus the number times the derivative of the vector. What is the derivative of the vector? So if you have a vector, and then as lambda changes, maybe you go to a different places, then the derivative is the rate of change as you move, as you increase lambda, how this vector changes, right? So the derivative as a rate of change will be like a velocity vector, which is also a vector. So that's why this derivative of a vector is also a vector. Derivative of an operator is also an operator, because the operator can be thought as a matrix, and every matrix element depends on lambda. Derivative of that matrix with respect to lambda is simply you take the derivative on every matrix element, because they are all functions of lambdas, and then organize them as a matrix again. So that's the meaning of this derivative of operators. Okay, so here is an explanation that this derivative of the state is basically the derivative actually applies to the state superposition coefficient. We are assuming that a set of state bases in the Hilbert space never changes, and what is changing with respect to lambda is actually the superposition coefficient. Okay, so now, so this formula, I think, is acceptable. It's just a direct consequence of this eigenequation. Assuming that the eigenequation can be evaluated at all different values of lambda, then you can take derivative on both sides. So now we just need to do another step, which is we just overlap these both sides with another basis state, which we label as M. And so we put this bra M state, and then we just overlap it from the left. So this upper formula becomes this one. And then in order to simplify this a little bit, so there's nothing we need to do for the first term. The first term will be there. And then the second term, there's some simplification we can do, because now H operator, Hamiltonian operator, you can either act on the right, on the n state, and then give you an eigenvalue times the state, right? But we remember that there is a dual version of this eigenequation, which is this H operator acting on a bra vector from the other side, and then it also equals the bra vector times the corresponding eigenvalue, because it's just a Hermitian conjugate of the above of this eigenequation. So with that, we can basically absorb this H operator into this eigenstate because we assume that the set of bases that we choose are always the eigenbases of the unperturbed Hamiltonian, which is this H. And then there will be a corresponding eigenvalue going out. So this will be the expression here, and then this is the next term where this n states also overlap with m, and then this is the final term. So now we can arrange the term a little bit because you can see this term and this term. They have very similar scalar product here, so we can factor them out. So this is the final expression. This expression is called HF theorem. And this expression actually contains two parts, which I denoted here. So because in this expression, n and m, if you take the scalar product between these two basis states, and previously we learned that these basis states are eigenstate of a Hermitian operator. Eigenstate of a Hermitian operator can be made orthonormal. So they form an orthonormal basis of the Hilbert space. And because of that, the scalar product is a chronic delta symbol, which means that only when n equals m, the inner product is 1. Otherwise, the two states are orthogonal, and the scalar product will be 0. So you can use that to replace this part. And then for the first term, the first part, this first order derivative of the Hamiltonian is simply the V operator. And the V operator, if you sandwich them between the n and m basis states, they simply take out the corresponding matrix element Vmn. So this is an expression that tells us how Vmn is related to the first order derivative of energy times some delta symbol plus the energy difference times some first order derivative of the state. So why this equation is important? Because this equation relates two things. On the left-hand side, the equation doesn't depend on the derivative of lambda. On the right-hand side, the equation depends on the derivative of lambda. Remember, what's our goal? Our goal is to compute the derivative of the eigenvalues and eigenstate with respect to lambda, right? So that's what we want to know on the right-hand side. So if we can have an equation that can basically relate those derivatives to something that doesn't depend on the derivative of lambda, then we have the hope to use this kind of equation to calculate the derivative, right? Without knowing what the function is, without knowing what's this E function as a function of lambda, we can still compute its first order derivative. For example, if you take this equation and set m equals n, so when m and n, they are the same. When they are the same, the first term, this delta symbol simply becomes 1. So there's a 1 here. So we pick up this term. But the second term, this term, when n and m, they are the same. They are the same state, right? Same state has the same eigenenergy. So these two eigenenergies are the same. Then their difference, energy difference, goes to 0. So the second term in this right-hand side completely vanishes, and we're only left with the first term. So in the special case, when m and n, they are the same state, then we basically arrive at a conclusion that the first order derivative of the energy eigenvalues is nothing but the matrix element of this perturbation operator. And the nth energy levels derivative will be related to the nth row and nth column, which is on the diagonal. This is the diagonal matrix element of the perturbation operator of the this V operator, and then it is nth diagonal matrix element in this V operator as a matrix, okay? So this tells us how to compute energy derivative, and this formula is called the first Hellman-Feynman theorem. There's a second one. The second one is the complement of the first case. The second Hellman-Feynman theorem is trying to concern the case where m not equal to n. So we just discussed m equals to n. There's another case where it's not equal. When it is not equal, it's also very interesting that when it is not equal, the first term vanishes. Because the first term has a delta symbol here. As long as m and n are not the same state, the inner product goes to 0, and then the first term vanishes, and we only care about the second term. And the second term, we can reorganize it a little bit. For example, it basically tells us this scalar product, which I write on this at here, and then it is related to Vmn, which is a matrix element in this V, and then divided by En minus Em, which is this formula. And similarly, you can also derive another formula by taking the Hermitian conjugate of this formula. You take this formula and then do a Hermitian conjugate or do a complex conjugate. When we perform complex conjugate, we basically interchange the two scalar product, which allows us to compute this scalar product the other way around. Okay, so that's the idea. So these are the very important formulas that allows us to evaluate, for example, the energy derivative and the state derivative in terms of something that does not depend on the lambda derivative, that only depends on those information that we can acquire at lambda equals 0, because this Vmn is the perturbation operator, which is the Hamiltonian evaluated, the first order derivative of Hamiltonian evaluated at lambda equals 0, and this E is basically the eigenvalues of the Hamiltonian evaluated at lambda equals 0. Okay, so everything on the right-hand side is what we know at lambda equals 0. So that's how we can use the knowledge at a single point, lambda equals 0, to infer something away from that point. Any questions? Okay, so these are the fundamental principles we are going to use to compute energy and state derivative. So once we know how to compute the energy and state derivative to the first order, of course, all these formula only tells us how to compute them to the first order. But then if we can somehow effectively reduce everything to expression that depends on lambda, that doesn't depend on derivative of lambda, if you look at these equations, both of these equations reduce the orders of derivative of lambda by 1. Right? On the left-hand side, we have first order derivative of lambda. On the right-hand side, it's zeroth order derivative. So all these formula effectively reduce the order of partial lambda by 1. So if we can keep applying these formulas iteratively, then we can imagine that eventually we will be able to calculate any higher order derivative, because we only need to keep reducing derivative of lambda orders by order until there's no derivative. So then that will obtain the result. So that's the idea. So let's take a look of this. Yeah, so this is the result. so for example, our goal is to compute the energy level correction. How does energy level eigenvalue, the nth energy level depends on lambda. And we know that as a result, the final expression must take this Taylor expansion form. We just need to compute all these energy derivative and then substitute the value into there. So the energy derivative, the first order derivative, we already know from the first Hellman-Feynman theorem, which is this Vnn, which is the diagonal matrix element of the perturbation matrix, or the perturbation operator. And we can continue to compute the second order derivative. And it turns out that the answer is here. I will explain how to obtain this answer in order to show you how to do this iteratively. And then that's actually hidden in this exercise. Let's take a look at this exercise. So for the first order derivative, we already know it's like that. So now we want to compute the second order derivative. The way to do that is you grab the result of the first order derivative and apply another derivative operator in front of that. So the second order derivative is to continuously take an addition derivative with respect to this expression, because this is the first order derivative, right? This V matrix is V operator is essentially the first order derivative of the Hamiltonian operator. And then if you try to take this derivative, then you can use the product rule again. The product rule says that the derivative needs to be taken for every factors. There are 3 factors here. The bra vector, then this operator, this derivative of Hamiltonian is still an operator, and then there's a cat vector. So we can take the derivative to the Bragg vector, to the Hamiltonian derivative operator, and then to the cat vector. But you can notice that the second term, the middle term, just vanishes, because the Hamiltonian, as we initially set up the problem, was supposed to be a linear function of lambda at the operator level. So there's no second order derivative of this Hamiltonian operator with respect to lambda, so the second term simply vanishes. So we only need to deal with this term and that term. We just want to compute them. The key step to compute them is to insert the very important trick, insert the resolution of identity. Because with this formula, you don't know where to go, right? Because it doesn't look like anything that is similar to where you can apply Hermann-Feynman theorem. So in order to apply Hermann-Feynman theorem, you need to have something like that. You need to have state derivative in a product with some basis, or the state derivative in a product with some basis. Where do you get that basis? You get that basis state for free from the resolution of identity. You can pop out the identity operator in here and then split the identity operator into a cat and bra basis and then summing over all the bases. So that's where we get this additional summation. So we can insert the resolution identity here, and then this term, if you still remember the second Hermann-Feynman theorem, it tells us how to compute the first order derivative of state and then in a product with a basis. And then the answer is here. If you look up the formula afterwards, you can check that. And then this part is also a second Hermann-Feynman theorem, which tells you how to compute that one. And what about these two? These two, the first order derivative of the Hamiltonian is nothing but the V operator, right? And then this V operator sandwiched between the M and N states, cat and bra and cat, is simply the matrix element of this V operator, which is VMN. So this will be replaced by a number as well. So now we have all these, everything reduced to an expression which doesn't depend on lambda. So using this idea, we can successfully calculate the second order derivative in terms of all this knowledge that we know at lambda equals 0. So you can imagine that we can continue this exercise, right? We can put, if this is the result, we can put another derivative in front of this result, and then this result every term will be expanded again as scalar product of operator with basis state, and then eventually the derivative will act on operator, will act on the basis state, and then you just keep playing this game, and then eventually we can basically obtain all orders of derivative. Although the computation will be very complicated, quickly become very complicated. So that's the idea. But I'm hiding something. Wait a moment. If you look at this result, it doesn't make sense because there's an energy denominator, you see? There's a denominator of energy difference in the, here in this expression. And this denominator seems to diverge when m equals n. Because I'm going to say that if I want to calculate the second order correction to this energy level, which is related to the second order derivative of that level n, I have to basically sum over all the level m, labeled by this m. And then in this summation, I'm going to sum over a fraction, and then this fraction has a denominator which depends on En minus Em. And then this energy difference between the nth level and mth level. But if this summation really goes through all the levels, and there is a point where this m coincides with this n, then this denominator will basically become 0, and then the fraction that we are going to sum over is going to diverge. So if you really use this formula to compute the second order derivative, no matter in which case, you will always get an infinity as a result. So that doesn't make sense, right? It never works. There's no case that it will work. So that's why we need to be more careful with this m and n summation. So let's redo the calculation again. This calculation is I did it too quickly. We actually need to redo the calculation, but the idea is very similar. Still, we need to insert the resolution of identity, but this time, instead of immediately apply the second Hermann-Feynman theorem, because you remember that the condition to apply the second Hermann-Feynman theorem is that n doesn't equal to m, right? When we derive the second Hermann-Feynman theorem, we make an assumption that n and m are different states. So you can't apply second Hermann-Feynman theorem to this state derivative immediately. Instead, we need to split this summation over m into two terms. One is the summation of all the other m that doesn't equal to n. And there's only one term that is missing. The only one term that is missing is this term. This term is the additional term where basically n equals m, which is this one. So okay, so with this one, then for the first part, for the first line where m doesn't equal, n is unequal to n, then we can obtain the same expression as previously we obtained. And then the missing term basically is here. And then you can also simplify this is like vnn. And then these two derivatives, you can see that they can combine because they can. This is a derivative of the n state and inner product with the n state. And then this the derivative happening at the first factor and the second factor. So that becomes the derivative of the scalar product of this n. But then the magic happens because the scalar product of n is 1, right? N is always a normalized state. So that becomes a constant. And because that's a constant, that you are taking a derivative with respect to a constant. Constant doesn't depend on lambda. No matter what's your lambda, your nth energy eigenstate. So your nth eigenstate will always be a normalized state. Although this state vector, as you tune lambda, will continue to rotate in the Hilbert space. But its length, the length of this vector never changes. And the length of the vector, or the norm of the vector, is simply this inner product. Never changes. It's always 1, no matter how you rotate this vector with respect to lambda. So the norm itself doesn't have a lambda dependence, and that's why this term goes to 0. And because of that, then we have the final answer. And you can see the final answer is so nice that it has a summation and precisely avoid the singular point where these n and m are the same and the whole fraction blows up. So using this very careful treatment, we can basically avoid all these singularities and then obtain the second order derivative of energy. So now all we need to do is to substitute all the answers into this Taylor expansion formula. The first order derivatives goes to here and become here. And then the second order derivative, which is an expression with a summation m not equal to n that goes to here, will combine with this 1/2 factor, canceling this factor 2. And then this summation goes to here. And then lambda square is copied down. So in this way, you can see, although we don't know what this function E of lambda is, we have successfully calculated its first order derivative and second order derivative, or in terms of those numbers which we already know at lambda equals 0. These are the energy eigenvalues at lambda equals 0. These are the perturbations that will apply at lambda equals 0. So we can really use our knowledge about lambda equals 0, which is the unperturbed Hamiltonian, and what is the perturbation, and using these informations to compute these energy corrections order by order in terms of lambda. So you can try to do higher orders if you want. I can guarantee that it's not an easy task. If you look up Wikipedia, there's people calculated all the way to 5th order. and then it's a very long formula. But let's not worry about that. Yeah. We only talk about the principles. So this is the energy eigenvalue corrections, okay? So similarly, we can go through the state corrections. It's also similar, but I will not go through the derivation again because first of all, you can, if you're curious, you can take a look at the derivation in this exercise. I can assure you it's not a very simple derivation. That's why I don't want to talk about it here. So you can click open this exercise if you are curious. But point is that using the similar idea, we can evaluate the first, for example, the first order derivative of the state is already there because the second Hermann-Feynman theorem tells us the scalar product of this vector. This is a vector, right? The scalar product of this vector with the basis m is simply this number, right? Then we know that if you have a state, which we denoted as psi, if you already know the scalar product of this psi with m equals psi m, then you know that this psi state is simply using psi m as a coefficient and superposition all the m's together. And this is the case here. The psi here is the state that we wish to compute, right? So we wish to know what is the first order derivative of the state, but the second Hermann-Feynman theorem tells us something about the scalar product of this derivative of state with the basis. So we just use that knowledge to infer what is the state. And the second Hermann-Feynman theorem tells us the derivative, the scalar product, or the linear superposition coefficient is given by this fraction, okay? And then we also need to make sure or take care of this n not equal to m stuff, because the second Hermann-Feynman theory is only applicable for that case. And then you can continue to take another order derivative and then do all the calculation. It's not very simple, but it's doable. And with that, you can substitute into this Taylor expansion and obtain the state correction. So following this procedure, we can essentially compute perturbative corrections to all orders. And if you are curious about higher order result, you can go to Wikipedia Perturbation Theory, which is partially written by me. And then I have all the formulas to higher order there. So, so that's essentially about the energy and state correction. Any questions? Mm-hmm. Yeah?
Are we assuming that basically the energy levels are non-degenerate as well?
Oh, that's a very good question. The question is about, do we assume that the energy level is non-degenerate? Here, yes. In this derivation, we'll assume that all the energy level are different because we assume that when the states are different, they have different energy. Otherwise, this term will blow up. But we indeed have cases in quantum mechanics where you can have two different states that has the same energy, right? And in that case, these formula are not applicable. So that's why the perturbation theory, time-independent perturbation theory, actually has two parts. Part one is called the non-degenerate perturbation theory, which deal with the cases. We'll assume that all the energy levels are non-degenerate. Every state has their own energy, and they never have the same energy. And then the second part is degenerate perturbation, and that is the next part. I think we will talk about that later, degenerate perturbation theory. But not today. So for today's discussion, all the energy levels are non-degenerate, okay? Yeah. And then let's summarize our result. The result is like this. So suppose we are given the unperturbed Hamiltonian H0, that means H0 can be written as a spectral decomposition in terms of its eigenstate and eigenvalue. Every Hermitian operator has a spectral decomposition of that. And when people write down a spectral decomposition, it means, or we are trying to convey the message that N is a set of eigenstates and form orthonormal basis, and E of N is the corresponding eigenenergy of this H0. And then when we write down an expression like that, we mean that V is an operator which we can expand or we can represent in this eigenbasis of H0. And then the corresponding matrix element will be VMN. So for H0, because it's represented in its own eigenbasis, so it's a diagonal matrix. So that's why we only care about the eigenvalue, which are the values along the diagonal. For V, because it's a perturbation, there's no guarantee that V will be in the same eigenbasis as H0. Otherwise, the problem will be too simple. So usually, V will not be a diagonal matrix. So that's why we care about all the matrix elements. That's why this V will be labeled by Mn. So this set of bases, the eigenvalue of this basis state, and then the matrix element of the perturbation are the three pieces of information that we know about the system at lambda equals 0. And you can see in this above expression, everything is expressed in terms of these three pieces of information. And in this expression, I have secretly replaced all this lambda times V by V. So the idea is like if you look at the above expressions, every time you have a V, you always come with a lambda. If you have 2V on the numerator, you come with lambda square. So we can always absorb lambda into the operator V. Because V is an operator multiplying by a constant, lambda is still an operator. So when we absorb lambda into V, we just assume that V is a very small operator. What does it mean by small operator? Meaning that it's a matrix whose matrix elements are very small. So we can, whenever we encounter V times lambda times VMN, we rewrite it just as VMN as if we absorb this coefficient into this matrix element, and then that the matrix element itself is very small. So when we think about lambda is small, we mean that the operator is small, meaning that the matrix element is small uniformly. And then in terms of that, we can simplify our expression by not writing so many lambdas. So that's why in the end, we will just write our expression in terms of the eigenvalue and the corresponding small perturbations. These are the small perturbations. So we are assuming that our perturbed Hamiltonian will be our original Hamiltonian plus some small operator. So this V is a small operator. And this formula tells us how to compute energy and the state correction in orders of this matrix element of V, which are small. And then using those corrections, you can reconstruct a spectral decomposition of the perturbed Hamiltonian. That means the perturbed Hamiltonian can be approximated by, of course, the approximation depends on how many order you compute. So if you can compute all the way to infinite order, it's an exact expression that it can be rewritten as this spectral decomposition, meaning that this will be the new eigenvalue, new eigenenergy, and this will be the new eigenstate. And both will be depending on the small perturbation V using the formula above. So that is all the summary part. And that's it for today. Thank you.